I am Raman Butta from News and Statics, and in this video I shall explain the mathematics behind the spread of the COVID-19 pandemic. So we've been hearing terms such as social distancing, herd immunity, the second and the third waves of the COVID pandemic, flattening the curve. All of them have deep mathematical and graphical underpinnings, which I shall try to touch upon in this video. So we have different epidemiological models for any infectious disease, and the kind of model that we shall be discussing is the SIR model. So essentially, under this model, the entire population is broken down into three compartments. Those who are susceptible, that means those who haven't contracted the infection but are prone to contract the infection in the future. Those who are infectious, that means those who are presently infectious, and those who have recovered. So this is the SIR model, and there's a constant mobility. That means initially, more or less the whole population is susceptible, and only one or two people are infectious, and then the susceptible people go into the infectious category, and some of them also recover. So this is the basic model. Now let's consider a certain individual who is infectious, and he affects people, a beta proportion of people around him. But there are only S number of people who are susceptible around him. So he'll infect beta S people per day. And just consider that this person takes, say, 10 days to recover. That means his recovery rate is 1 upon 10. So this quantity is called gamma, and this quantity is called 1 upon gamma. That means we know that this quantity is about 14 days for the coronavirus, that he remains infectious for 1 upon gamma days. So essentially, he transmits this disease to beta S times 1 upon gamma people throughout the period of his infection. This quantity is known as the reproduction number R. This S actually becomes the total population N at the beginning of the pandemic, just as I've discussed. At that time, R assumes the maximum value R naught, which for the coronavirus is about 2.4, but it definitely varies because the kind of social distancing that different societies have is different. So we have this value of R naught, and then as time progresses, this N value is no longer N, it becomes S, it keeps on decreasing, the S value keeps on decreasing, and so R value also keeps on decreasing with time. So initially it is 2.4, it becomes 2.3, 2.2, 2.1, 2, 1.5, 1, 0.5, it will keep on decreasing. Okay. So once this concept is clear, this concept of R equal to beta S upon gamma is a very important formula. At this point of time, I would also like to say that at the beginning, R naught is equal to beta N upon gamma. But for purpose of convenience, sometimes we take N equal to 1, and we take everything else as a fraction of 1. So then we can say R naught is equal to beta over gamma. Please remember this equation. I'll erase it. So please remember it in your head that R naught equals beta over gamma, which is 2.4 approximately for the COVID pandemic. Now, when I make this diagram of the SIR model, then the following rates illustrate the mobility between the different compartments. This is beta IS, understandably, and this is gamma I. So I can write two very important differential equations. One is that ds over dt is equal to beta is, negative because it is decreasing, and di over dt is equal to plus beta is minus gamma I. So if this positive component is greater than the negative one, di over dt is positive, otherwise it is negative. So I can actually write this thing as I multiplied with beta s minus gamma, which I can write as I multiplied with I into R gamma minus gamma, because I already know that R is equal to beta S over gamma. I've just discussed that. So I can write this thing in this way, and this means it is equal to R minus 1 times gamma I. So just by seeing, you can understand that this is an exponential form because di over dt is proportional to I, and therefore you might be prompted to write that I is some I naught multiplied with exponential of R minus 1 gamma t. But this would have been true if r minus 1 is a constant. But just as I've said that s keeps on decreasing, and so r also keeps on decreasing with time, and it's not a constant, so we cannot write this equation. But still, just remember this equation for the purpose of convenience. We'll try to analyze, if we consider r as more or less constant, we'll try to analyze the graph of I with respect to t. So let me write it again. I equal to some I naught times e to the r minus 1 gamma t. That means this, when I plot the graph of I versus t, there's some initial value I naught, and then it keeps on increasing exponentially till God knows when. But this does not happen. R keeps on decreasing, and as soon as r becomes less than 1, that is r minus 1 becomes negative, this exponent becomes negative, and it is no longer an increasing exponential. It becomes a decreasing exponential. In fact, the rate of increase of this exponential also keeps on decreasing, and that's why we have a bell shape at this point. And at this point, in fact, we can observe by this transition that it will start decreasing. So this is the threshold point. And when the exponent starts decreasing, we can no longer say that the pandemic is spreading. This is therefore the point of herd immunity. Even if we consider the di by dt equation, which is equal to your r minus 1 times gamma I, we can understand when r equals 1, this becomes 0. And if we take the second derivative, we'll find that it becomes negative. Therefore, this is the point of maxima. In fact, if we plot the graph of di over dt with t, then it will have some initial value, then it keeps on decreasing, and at this point, when r is equal to 1, it cuts the x-axis. Then it again keeps on decreasing, but what happens is that the entire infectious population is exhausted. All of them become recovered, and at that point of time, there's no more di by dt variation, and it stops. So this point is actually the threshold point of herd immunity. What's important to understand is essentially that the susceptible population is decreasing. We very well know that the susceptible population is decreasing. So when r equals 1, we can do the following mathematics. We already know that r equals beta s times beta s upon gamma. But when r becomes 1, that means that when at okay, I think I was confusing a little bit. So r equals beta s upon gamma. But at this threshold value, r threshold is equal to 1, which means that beta times s threshold upon gamma is equal to 1, which means that s threshold is equal to gamma upon beta. But we have already seen previously that beta upon gamma is r naught. So this value is 1 upon r naught, which for COVID is 1 upon 2.4, which comes out to be roughly 40%. So when the susceptibles fall to 40% of the population, that's when herd immunity will set in. That means the number of immune people must be 60%. This must be the number of immune people. So if I actually draw the graph of I versus t, and it increases in this way, and then it decreases, the peak comes here. So this area, which signifies or symbolizes the number of immune people, should actually be 60% of the population. This is a very important thing. This is the very important concept of herd immunity. So what's the problem? The problem is the following. If we allow 60% of the population to become infected, and only then the disease will start decreasing in the population, God knows how many lakhs and millions of people will die in the process. Moreover, there's another problem. This horizontal line actually signifies the carrying capacity of the hospitals. So the hospital will not be able to take the load of more than this number of patients, say IH number of patients. So at this peak point, the patients who are suffering from COVID at the present time are far more than IH. And so these people will surely meet inevitable death if their own immunity is not that high, because they will be deprived of hospital support. And that is the worst thing that can happen. So therefore we have two objectives. First is to decrease the height of this peak, and then is to postpone this peak so that we can buy time in order to develop some vaccine or to generate more awareness or our own resources. So there are two purposes, and I shall write it down because it's very important. One is to delay the peak, which symbolizes herd immunity, and secondly is to reduce the height of the peak. Now let us see how can we actually achieve these twin objectives. So when we see this graph, we know that if we do some social distancing, we can do it in two ways. Either we can decrease beta or we can increase gamma. Okay? If we decrease the value of beta or we increase the value of gamma, in both the cases, the value of R equal to beta S over gamma will decrease. Okay? So I won't touch upon gamma. Of course, if you do quarantine, then the effective value of gamma is increased. But if you do social distancing and lockdown, your beta is decreased effectively. So if we do decrease the value of beta, please try to understand in this graph that what really happens. When beta is decreased, I already know that R naught is equal to beta upon gamma. So if my beta is reduced, then R naught, initially it was 2.4, now it might have become 1.7. So just a second, let me erase these things. Okay. So initially R naught is 2.4, but now because I have reduced beta by means of social distancing and lockdown, my new R naught is say 1.7. And so you might think that the time it takes for 1.7 to come to 1 would be lesser than it would take for 2.4 to come to 1. In other words, the peak would be advanced rather than being postponed. But you are wrong, because when you do this social distancing and you reduce the R naught, the rate at which the susceptibles reduce will vastly be slowed. And so R, which is equal to beta S upon gamma, will decrease very slowly, because the S value is decreasing very slowly because of social distancing. And therefore it will take more time, considerable time, for R to become 1. And therefore, just a second, yes, therefore the peak will surely be delayed. Instead of here, the peak will be somewhere here, for example. But will the height of the peak also reduce? Yes, because you see, when the peak is delayed, then the x-axis coordinate increases. Okay? If the x-axis coordinate increases and the y-axis coordinate also increases, that is, the peak is say here, sorry, I'm not making a good diagram. Yeah, the peak is say here, that is, the x and the y-axis coordinate both increase. That means the number of people who are infected also increases. But that is not the case, because we know that when the R value is reduced, then definitely the 1 upon R value is increased, which is equal to the S threshold. And the number of immune people, which is actually 1 minus 1 upon R, will decrease. So if the number of immune people have to decrease, then definitely the height of the peak will have to be lesser, far lesser. So the height of the new peak will definitely be lesser, and it will be somewhat like this. So the peak is now coming here, and the curve is flattened. So our twin objectives have been achieved. Now what happens is that even after this peak has come, say at this point, the people who have become immune is 60%. So after this point, if you open the lockdown, there would be no problem. if at this point you open the lockdown, the curve will still keep on decreasing in some exponential value. But if this area is not 60%, because you have actually fooled the virus to think that this is a less infectious disease, you have decreased the value of R0 and R, but actually it is not. When you ease the lockdown, or when you ease the social distancing strictness, then the following thing can happen. If beta is say 0.7 and your new beta you have decreased during the lockdown to say 0.3, okay, now when you ease the lockdown and you increase the beta value, so beta post lockdown, if you make it say 0.5, and if it is too much, so that the R, which is beta S times gamma, actually becomes greater than 1, then it will again start increasing exponentially. So this thing will be called a second wave. Okay. In case instead of 0.5 you increase it slightly to say 0.35, then if R has dropped down to 0.8, it might increase to 0.95, and it is still less than 1. So instead of dropping at this pace, it may start dropping at a more gradual pace, but it will still be dropping as long as R is less than 1. But if you increase beta too much, then R minus 1 may exceed 0 and it will again start rising exponentially. You understand? So we must be very cautious. The government must be very cautious in easing the lockdown to ensure that a second wave does not happen. And even the unlock has to be done in phases. So if the graph is decreasing in this way and you do the unlock 1, then it may decrease in this way. Then you do the unlock 2, then it may decrease in this way. So it is decreasing. But if you increase the value of beta too much, then instead of decreasing, it might start increasing. And that is a second wave. We should avoid a second wave, because when a second wave happens, it might again increase more than the IH value, and that will be a terrible thing. If we develop a vaccine, then all of a sudden the number of susceptible people decreases, because most of them who are vaccinated, they become immune. And so the number of susceptibles decreases dramatically. And in a very short period of time, they will decrease less than 40%. And instead of rising, the curve will sharply decline. So that's why vaccination causes the curve to sharply decline. But vaccination is not so easy. So until that time, we need to flatten the curve, and we need to ensure that the unlock happens in phases so that a second wave is avoided by way of increasing the beta value too much. So this is all for now, and there are actually so many aspects to this discussion. I shall come up with some other topic. So stay tuned to News and Statics. Subscribe to the YouTube channel of News and Statics. Like our page on Facebook, and share this video with as many friends as possible, so that the knowledge is spread and people become more aware of this disaster. People actually understand that how important social distancing is, and not to become carefree and cause a second wave to happen. This has to be avoided. Flattening the curve is a gift. It's like buying time, and we should use this time to develop vaccines, to become more aware, and to take all kinds of precautions possible. So this is all for now. Meet you again another day with another topic. So until then, bye-bye.